on diode-pumped alkali lasers. Okay, we are recording now. So what I'd like to talk about today, I want to start out by talking about these things called derivative coupling terms and why we need them, why do we calculate them, what are they used for. This isn't going to be everything I want to talk about today. And if you're interested in learning more about it, this is largely what I'm going to give the mini course in a few weeks at the end of November in derivative coupling terms. And that I really want to try to teach in Portuguese. So if you don't do the English that well, then we'll kind of meet halfway for that mini course. I will do Portuguese not that well, and you can listen to me in Portuguese, and we will try to learn and teach together. I also want to talk a little bit about the software Columbus package. It's a quantum chemistry package that we use, show some of the results we've gotten with it, some of the things I want to do with it. And then I want to talk about a three-body problem for the diode-pumped alkali laser and some of the things I would like to do with that. And then I've already talked about my other experiences today, so we can cross that one off the list. All right, so talking about these derivative coupling terms, non-adiabatic derivative coupling terms, they are a link between nuclear motion and electronic motion, electronic energies. And we'll see why that is. I'll try to explain what that link is. We're going to start off with the time-independent Schrödinger equation here. And so hopefully this equation here looks very familiar to you if you have a background in physics. The time-independent Schrödinger equation. So this part right here is the kinetic energy operator, the nuclear kinetic energy operator. This piece right here is our nuclear potential energy operator. And that actually has buried inside it the eigenvalues from the electronic Schrödinger equation. So they are buried in there. And then we have our eigenvalues. And of course our wave functions. All right, so hopefully this looks a little bit familiar. And I'm calling this the Born-Oppenheimer approximation, and I will make that clear why that is in just a minute. So going on to the next slide here, what I'd like to do is kind of take that and expand it as kind of a matrix so we can see what that looks like. So we have some identity matrices, so those are pretty easy to expand. And we see what we get is that in the kinetic energy operator, the T sub n, we get the derivatives with respect to nuclear coordinates all along the diagonal. And then our E matrix, our potential energy matrix, again, it's different values, but they're all along the diagonal. And then finally our eigenvalue, this is just an eigenvalue times the identity matrix, so that ends up just being along the diagonal there. And this is a very nice system of equations to solve because there's no off diagonal elements, right? Everything off diagonal here, these are all zeros. And so while we have in equations here, they're really in separate equations, right? Because there is no way to get from one equation to another equation. They're all completely separate because all the off diagonal pieces are zero. We're going to use the term adiabatic. And this is the adiabatic representation because adiabatic means it doesn't leak, right? It's not going to vaziar. So you can't hop. There's no way to hop from one energy surface to the other because there's no off diagonal elements. And why is this important to be able to hop? So let me give you a quick example here. If we're thinking about a molecule or a scattering, let's say we have maybe we have the energy here, and I'm going to draw some energy surfaces. So maybe we have something that looks a bit like this, and we'll call this R, meaning the distance between, let's say we have two atoms, because that's really what I'm going to talk about today, a system of two atoms. And we have some, the first energy level here, and maybe a second energy level here, and a third energy level here, right? So we could find ourselves somewhere on our system might be on one of these. Let's put it on the high energy, right? And maybe we want to get it, or interested in, can it get to another energy level? How do we get from the top to the bottom? Well, normally, and especially when we talk about lasers, we talk about radiative transfer. So we have a time-dependent piece of the Hamiltonian, something that can stimulate the emission, right? So we get this jump, and out comes a photon. And this photon carries away the energy that we lost from the electronic transmission. That is radiative. Right? Now, on the other hand, and sometimes this happens, and this is why we might be interested, is maybe we're up here and we can get down here, but there's a mechanism to do it without radiation. And so this is, in blue, we're talking about non-radiative transfer. Okay, and this is something we're interested in because it happens in real systems. And if we just look, and of course no photon comes out of this, because instead of being radiation, well, clearly we're losing energy from the electron going from one potential energy surface to the other one. But instead of losing that energy in the form of a photon, that energy goes into nuclear motion. So now the atoms themselves speed up, and we don't get a photon. So when we're talking about non-radiative transfer, we cannot model that with this adiabatic system, because there's no way to get from one surface to the other one. We cannot model that. We can only model radiative transfer with this. So that is why we need what we call these derivative coupling terms. So take a look at, notice what has happened here is that we've taken once again, we have the kinetic energy operator here, and we've added to it this extra piece, this P matrix. Okay, that P matrix is going to have our derivative coupling terms in it. Now today, I'm not going to talk about how we came up with this, where this P matrix came from. Consider that a little bit of a tease for taking my mini course in a few weeks. We'll talk more about what is the origin of these derivative coupling terms. But for today, we're just going to say we know that they're there, that this is an extra matrix in here. This, by the way, altogether, this is called the gauge covariant del, or derivative operator. It's not just the del on its own, it's the del plus the P. And again, not going to talk too much about that today. We'll talk more about what that means in the mini course. Okay, so we add this P matrix full of the derivative coupling terms, and what that P matrix looks like is it's got zeros on the diagonal. The off diagonal, we still have these dels, these derivatives with respect to nuclear coordinates, but they're actually taking derivatives of the electronic wave function. So this is kind of the kicker here, is this is a derivative with respect to nuclear coordinates, whereas what it's taking the derivative of is an electronic wave function. Or if you're familiar with electronic structure theory, and if you're going to take Professor Lischka's mini course here, I think it's next week or maybe the week after, configuration state functions are what we will be taking derivatives of, okay? But suffice it to say, we now have these off-diagonal pieces here, and we're now moving into the diabatic representation, because now that we have these off-diagonal pieces, right, this P matrix gets added in to this diagonal del matrix, and now we do have off-diagonal pieces, and these off-diagonal pieces can couple the surfaces. I'll kind of zoom out there so you can take a look at everything together. Okay, so what do we know so far? We know these derivative coupling terms exist. This is, in fact, what we calculate using something like Columbus. Columbus is not the only software package that can calculate derivative coupling terms, but it is one I like to use because it is very accurate, and it can do it at a high theory level. We like to do it at the multi-reference configuration interaction. So we do this, if you've heard MRCI, multi-reference configuration interaction. And I won't talk too much about what that means. I think that Hans will talk more about that when he does his mini course, and some of you may already be familiar with that. But that's why I like to use Columbus. So we know how to calculate these, or we can calculate them, and the question is, why do we need them? What does this do with solving the problem of how do diode-pumped alkali lasers work? So I will talk briefly about that, these nuclear dynamics calculations. So up till now, I've been showing you the time-independent Schrodinger equation, and of course, all my physics friends will know that there's a time-dependent Schrodinger equation as well. And when we have the time-dependent Schrodinger equation, we get solutions to that if that look something like psi of t is going to be something like e to the minus I over h bar, and the Hamiltonian we can break up into a kinetic piece and a potential energy piece. Right? And since those would be added in the exponent, we can break them up and multiply them as separate exponentials. And that would be multiplied by some initial wave function, right? And if we want to talk about doing this computationally, then we're going to be doing finite steps of delta t. So we might say instead that if we want the t plus a delta t, then we would put a delta t and a delta t, and this would just be t. So we can step forward from step t to t plus delta t. Now, if we look at this equation, we're exponentiating operators, or we're exponentiating matrices, right? And that's always a pain. The best way to do that is when they are diagonal matrices, because then we just put the exponents on the diagonal. But let's take a look at these operators we have here. We've got the kinetic energy operator. And remember, this is really just a fancy version of the momentum operator, right? It's p squared over 2m. And the potential energy operator is really just a fancy position operator, because potential energy is just a function of position. Well, of course, my physics friends know that P and R, or P and X and Y and Z, however you want to call it, don't commute, right? We can't have momentum, we can't know momentum and position at the same time. And so we cannot diagonalize this matrix and this matrix at the same time. And that's bad for us because that makes the calculation very difficult. However, There's a technique, and again, I won't go too much into this technique. It's called the split operator method. Some of you may already be familiar with it, for propagating a wave function in time. And really quick, basically what we do to do the split operator method is we take our psi at some time t, and we're going to do, since it's already, we're going to assume it's in the position representation, and we're going to do kind of this half step of multiplying by half of the potential energy operator. And I've not given myself enough room here. Because if we start in the position, and if we look back here, the position representation, and if we start here in what looks like the adiabatic matrix where we're completely diagonal, hey, that's good because we can exponentiate that. What we then do is we take a Fourier transform of this and put it into momentum space. We can then take the kinetic energy operator, oops, changed color there, and we're going to do the whole kinetic energy operator and multiply it. Now, when we are in the momentum representation, what we can do is we can use this form of the operator. Now, how did I get from here to here? There's a transformation I can do to diagonalize t. And really, it's del plus p. That's what we're diagonalizing. Well, in order to do that, I just have to know what these terms are. If I know this matrix, then I can figure out what the transformation is to diagonalize that matrix. And then I get a diagonal kinetic energy operator at the expense of now I have a non-diagonal potential energy operator, and I've introduced these coupling terms, these coupling surfaces. We think about these as potential energy surfaces. And before, right, we just had very easily a number of energy surfaces that this system could be on. We now have these. They've changed a little bit, but the other thing that has happened is now we have these off-diagonal coupling surfaces that tell us how much one surface wants to go to the other surface. But the important thing is now T is diagonalized. So when we come over here to our split operator method, we now have a diagonal T. We can use that version. And then the rest of the split operator method is we do an inverse Fourier transform of that, and then we do the rest of the potential energy operator. Again, I'm just showing you this to show you why we need to know what these derivative coupling terms are. We're not going to do any of this today. Okay, so effectively what we're doing as we proceed in time, doing our dynamics time step by time step, is we start and we want this, and we want a diagonal potential energy piece. But then we do our Fourier transform and we need to get to use now this form of the equation with a diagonal kinetic energy piece. And as we step forward in time, we just keep going back and forth and back and forth. And this is why we need to know what these derivative coupling terms are so that we know how to do this transformation and get this matrix right here so that we can do these nuclear dynamics. So that's the motivation behind why we want to calculate these potential energy, or excuse me, these derivative coupling terms and why they're important to nuclear dynamics. Now, of course, the topic of this is specifically has to do with diode-pumped alkali lasers. And the reason is because this is what's going on inside the lasers. If I go back to my terrible drawings of energy surfaces, what we have when we do diode-pumped alkali lasers is we have an alkali metal. It could be, let's just say, potassium. And we have some noble gas, we could say helium. right? That's just one selection. It could be many that, that we can use in this laser. So in the potassium, as you know, potassium, the alkali metal, it's in its ground state, it's going to have an electron, a single electron in its outer S shell. We can excite that outer electron, that valence electron, into the P shells, and there are three P's to choose from, right? An X, a Y, a Z, or we could say a 0, a -1, a +1, however you want to say it, right? But we can excite these, right? And so if we looked at just the K, just the potassium, we might say it's got these, it's got these energy levels. We've got the ground state, we've got our three P's, right? And these are actually split relativistically. They're split by the spin orbit piece of the Hamiltonian. And so we have a couple of pieces that are going to have different symmetry and different spin. Actually, these two in the limit, these two kind of come together. And we have these, so our idea here is what we want to do is in this laser, we want to be able to pump things up from the ground state to an excited state. Those excited state potassium atoms then need to come down to a lower level in this P manifold so that they're all ready in the end to do a radiative transfer to give us our lasing. So this part in green is radiative, but this part in blue up here, if I zoom in a little bit, this is non-radiative. Okay, so that's what we need to get to work. Now that's just K on its own. When we add helium into the mix, of course, now we can have a distance between them. And so our P manifold might look like this. And now what we have, instead of calling them generically E1, E2, and E3, and of course we've got the ground state down below that I'm not quite showing here, but you know, this is going to be the A2 pi 1F, I believe. There's going to be an A2 pi 3 halves, and then a B2 sigma 1/2. And if you don't know what those things mean, that's okay. These are just chemists' terms for the symmetry to tell us which level is which. So basically what we're doing with the diode pumped alkali laser is we are pumping with the pumping mechanism. We are getting the system from the ground state way up here into this excited state. As the potassium and helium in this example come together, the system moves up on this curve, right, as R gets smaller and smaller. At some point, or over some period, we are going to get this non-radiative transfer from the sigma 1/2 down to the pi 1/2. And that is when it is going to be ready to now come back out as the helium goes away. And then once the potassium is all on its own, we can lase with it and we can stimulate it to fall back down to the ground state. Okay, so this is the process, why we're interested in what's going on in this part of the physics. When we bring that helium close to that potassium, how do we know about what's happening? How does it get from that top level in the P manifold down to the bottom level? So that's what we're trying to model here. Okay. And this is what we use Columbus for. Now, I know you can't click on that link in this presentation, but it's there for you. And if we distribute the slides afterwards, you'll be able to click on the link in the slides. I just put a little blurb here. This is from their website. Obviously, there's a lot more to know about the code than just this, but it's high-level ab initio software, mostly for doing multi-reference calculations for ground and excited states, right? And Columbus is free for anyone to use. You can go and talk to Felix Placer, and he will get you into, I think it's in a Git repository where you can download it. There's a copy of Columbus here. Professor He+He has a copy. I use a special copy, and I'll talk to you more about why that is, that I use in the United States on the Defense Supercomputing Resource Center. But this is something that everyone can use. And when Professor Lishka comes next week, he will be talking, I believe he will be talking about Columbus. I think he normally does. And so you could learn more about Columbus through his mini course. In this slide, I have a few of the things we have done just to show you. Hopefully you can see, if you look all the way to the right, now you start to see these curves, kind of what I attempted to draw up above. This is in fact potassium plus helium. But you see on the left, figure 2 as it is here, these are derivative coupling terms for potassium plus helium, the radial ones, that we calculated a while ago in Columbus. And on the right side, figure 4 as it's labeled here, you see some of the energy levels. Now you see more than you might expect to see, right? You think there should be 3 in the P manifold, and of course there is a ground state way down here, ground state. But what I want to show you is, so if we look at this one right here, and this one right here, and this one right here, those 3 are the adiabatic surfaces. So those are the ones we get when we just do an energy calculation, the ones we get from above. But once we have these derivative coupling terms, and we do that diagonalization of the kinetic energy operator, remember that potential energy operator, those diagonal pieces change. And we also get off diagonal pieces, which I have not shown in this picture. But what happens, now this middle one, this 2p3 halves, that doesn't change because of its symmetry. It stays the same. It doesn't mix. But what we get is that the pi 1/2 down here, it shifts and it starts to look like this. And I got this one mixed up here. This one was the original one, and it is shifting down just a little bit to this new one. So we see these shifts in the potential energy surfaces as we take into account the derivative coupling terms. Here, all the way on the left now, this is just another example of a calculation we did, published a little bit later, that is lithium plus helium. So a little bit simpler calculation. And this one does start to show this coupling surface here, right? And that is, again, that off-diagonal piece of the potential, the diabatic potential energy operator. Okay. Now, these were done not with the vanilla Columbus that you can go download. We actually had to do some changes to Columbus because, as I mentioned before, the separation that we get between these states for an alkali metal plus a noble gas, that separation happens all in the spin orbit operator. And while Columbus, as it is now published, it can deal with spin orbit wave functions, and it can create, or it can calculate derivative coupling terms. It cannot currently calculate the derivative coupling terms of spin orbit wave functions. So this is something we have added to kind of an experimental version of Columbus that we have in the United States. And then this, Dave Lewis took those potassium plus helium derivative coupling terms that I showed you. He also calculated Coriolis derivative couplings, which I won't talk about today. And he came up with a scattering cross section. So he actually did those, the split operator method for calculating the nuclear dynamics, and came up with the scattering cross sections, which you see here. The difference between the red dotted line and the red solid line are whether you do or don't consider the Coriolis coupling. So just know that the answer is probably somewhere in between there. And there are a couple of previous calculations from other people that are in that range as well. So this is things that have been done in the past. What I would like to do with Columbus, as I said, we have kind of an experimental version that's good for calculating derivative couplings for spin orbit wave functions like we need in diode-pumped alkali lasers. I want to continue the effort to integrate that into version 7, the current version of Columbus. Between version 6 and version 7 of Columbus, there was a large structure change, so it's not a simple cut and paste. There's going to be some amount of effort to go in and make all the changes. I currently have a contact at the DoD's High Performance Computing Center, and we are proposing getting their help to make this happen. Some interesting things we've seen before is that, so this is a piece I won't go into right now, but I will talk about in my mini course, is that if we sum up all the antisymmetric derivative coupling terms can be split into a symmetric and an antisymmetric piece, just like any matrix. The antisymmetric piece should, if we add them all up, should add up to be the electronic momentum eigenvalue. But right now they don't seem to be. So the question is there another reason why they don't add up? Is it just a bug in the code that we have to track down? I don't know. So this is something that we need to do. I would like to do that as well because Dave Lewis, who I mentioned before, who did the dynamics calculations, he came up with an estimation method for derivative coupling terms. And one thing we would like to do is compare his method to our method, which we've already done for the radial derivative coupling terms, but not for the Coriolis coupling terms. So this is an important step to make that comparison. Now recently, here's some recent results. About a year ago, the folks that are interested in diode-pumped alkali lasers said, we know you've been looking at the excited states, but is there any coupling to the ground state? And that's a very good question. So about a year ago, I started looking for coupling between excited states down to the ground state. And sure enough, there is. So if we take a look, for example, at this first one, this is potassium plus helium again. You see here, this looks like what we saw a couple of slides back, and that's that radial derivative coupling term between the excited states in the p manifold. Okay, down here what we see is a derivative coupling between the ground state and the sigma state, and it is not as big as the one that's just the excited states, but it's certainly not insignificant, right? So this is something that tells us that maybe we should consider the ground state coupling. Now, obviously, as we get very close to together, all of these couplings start to blow up because we're just so close together. The chances of getting that close together are very remote, so we don't worry too much about that, about this range over here. But, you know, up to a couple of angstroms, that's certainly possible. And here we see with potassium and neon, a different noble gas, and potassium with argon. And they all have a same characteristic shape to them, a little bit different each one, but they all show that there is significant coupling to the ground state. And here below, what we have is just a comparison. This is what I alluded to earlier of what we've calculated for these radial derivative coupling terms and what Dave Lewis, he did an estimate. So they're kind of close, but there are some differences. And then the next couple of slides just show a few more different species. So here we have rubidium on the left with helium, on the right with neon. And as you can see, that ground coupling still significant, still not insignificant, still not as big. And we see some divergence from Dave Lewis's estimation. And here again, here is cesium with, again, on the left helium and on the right neon, and we see those same kind of patterns. Okay. Now, one thing we found, again, in the Columbus code was there was an error in how it was doing the anti-symmetric piece of the derivative coupling term. So this winter, I had been working on correcting that, and I believe I have. And one thing to note, so here's rubidium plus helium, is above, those graphs I showed you above were only the symmetric piece. When we add the anti-symmetric piece, it looks like we get, it actually takes away from the coupling. It makes less coupling. And that black line is, again, just the Dave Lewis approximation. One thing that other folks have talked about is that derivative coupling terms, just because of the fact that we have incomplete basis sets when we do quantum chemistry, there's always a little bit of something left over. And what we find is that the derivative coupling terms should be symmetric. That is, if we think about, if here's our, let's say this is potassium and this is helium, right? If potassium moves this way a little bit, we should get the same answer as if helium moves this way a little bit, but we don't. And that comes back to just the mathematical limitations. We get a slightly different answer. However, there are these things called electronic transfer factors, which are supposed to take that into account. And if we add those in, then we would get completely symmetric. What one scientist said, and I don't have his name off the top of on my paper here, is that the calculation is that those electron transform factors are exactly equal to the anti-symmetric derivative coupling term. So effectively, we should be able to get rid of the anti-symmetric piece. They're equal and opposite. Now, he was talking about bound molecules and not necessarily scattering. We're doing scattering here. So I don't know. I have to do more research into finding out if that is valid for what we're doing or not. Now, previously, we were just doing the excited states. And so if you only coupling two excited states, you get one off-diagonal piece, right? If we get D11, D12, D21, D22, right? And that's our diagonal piece. And obviously, there's other diagonal energy levels, but we're not too concerned about those ones. Well, now if we say we're going to couple the ground state as well, we now have to expand this to D13, D23, D33, and so on. And so we actually get 3 separate coupling surfaces, which I showed, I've calculated here. And again, the coupling to the ground here and here, these aren't as significant as the excited state coupling, but they're still there. And so I was able to put those together and do a little comparison. And again, what we'll see, for example, the sigma 1/2, the adiabatic is this one right here. When you consider only the excited state coupling, you get this right here. But then when you also consider the ground coupling, you get something that looks like that. So there is a significant change in the potential energy surfaces when we consider this ground state coupling. And finally, one thing I wanted to talk about real quick, and I know we're just about out of time here, is the fact that USAFA, the United States Air Force Academy, which also does DPAL research, back in 2012, they turned up the pressure of the helium, right? And what they found was there was not this linear relationship between the collisional mixing rate and the pressure of the helium. They found there was a little bit of a curve to it, and they suspected that there is something going on with 3 bodies that maybe let's say, I think this was rubidium, that rubidium might be interacting with 2 heliums at the same time if there's more higher density, and that's giving an increased rate. So one thing that I was working on, and this work stopped about a year ago, but I might be able to pick it up at some point, was doing the 3-body interactions. And so this is just an example. This is the coupling. This is only considering the excited states, but the coupling between rubidium and 2 heliums. And as an example, an interesting example, if you look here all the way on the right, if we just consider rubidium and helium plus helium and helium, we get this interesting thing going on. So we have right here in the middle, we've got this in one of the excited state, or one of the energy states, potential energy surfaces, we have this crest. Looks like something that normally wouldn't be allowed. It's going to push things away. But when we consider the three-body, we actually get a valley. So there's a difference between what's going on between if we just thought about two-body and we thought about three-body. And clearly, if this is, of course, going from the adiabatic to the diabatic. But either way, it's interesting when we start to look at the three-body interaction versus the two-body interaction, the differences we see. So this is a work I was working on. I stopped about a year ago because I ran out of time to work on it. This, by the way, was done in MolPro, a different method, and I used Dave Lewis's approximation method. What I'd like to do is do this, at least for some specific interesting geometries, in Columbus, to see how the calculated rubidium plus helium derivative coupling terms and coupling surfaces compare to those we estimated, to see if that Dave Lewis approximation method, is it a good extension to three-body, or does it fall apart when we hit three-body? So really, in conclusion, there's some projects that we want to do to support understanding the quantum operation of diode-pumped alkali lasers. So I talked about finding why it is those antisymmetric derivative coupling terms don't match the electronic momentum operator. Is it a bug? Is it something more? We want to do the big effort of updating Columbus 7 for spin-orbit derivative coupling terms. Explore more of the differences between the Dave Lewis approximation method and what we've calculated. Maybe we can find a reason that they don't match up. Finish these three-level derivative coupling calculations like the ones I showed for rubidium helium. I'd also like to do potassium helium, cesium helium, etc. We can then perform dynamics calculations with these three-level derivative coupling terms and see how they compare to just the two-level derivative coupling term dynamics calculation that Dave Lewis did about a decade ago. And finally, this big project of performing the three-body calculations instead of in MolPro, doing them in Columbus and seeing how those compare. So these are a lot of the thrusts I have for working on diode-pumped alkali lasers that I'd like to work on. If someone is interested in what I've talked about, maybe we could work on these together. This work is done in collaboration with the Air Force Institute of Technology and the Air Force Research Lab. Well, that's all I have today. So I guess I can open it up to questions. If you ask in English, that would be great. If you ask in Portuguese, just please ask me slowly and I'll do my best to answer.
Lachlan, thank you very much. It was really, really interesting. E é claro, os alunos, agora está aberto para perguntas, né? Como o Lachlan falou, as perguntas podem ser feitas aí em português ou em inglês. Se qualquer coisa, a gente ajuda aqui a traduzir para o inglês, ou vice-versa, traduzir do inglês para o português, a gente vai fazendo esse papel aí do meio. Só vou pedir aí para levantarem a mão, acho que no Google Meet tem como levantar a mão, não lembro.
Desculpa aí, você esqueceu da salva de palmas.
Opa, verdade, André, obrigado. Pela questão de ordem aí, né? Pessoal, vamos abrir o microfone para agradecer o Lachlan aí. Uma salva de palmas aí para ele. Obrigado. Bom, e agora estamos abertos às questões aí. Bom, enquanto... Lachlan, tem uma coisa que eu estou bem curioso, na verdade, para saber. Eu vou até tentar perguntar em inglês. You were talking about this non-radiative surface hopping, right?
Yes.
The non-adiabatic approximation allow this. But do these surface hoppings still obey the selection rules or can break the selection rules?
As far as I know, they still have to obey selection rules and have to respect symmetry, for instance. And one thing we found, for instance, was there was no coupling, or the coupling to the 2 pi 3/2 state was effectively 0, showing that it did respect the fact that those selection rules regarding symmetry are still obeyed.
Okay, nice. And do you know, for example, if we have a change from the triplet to a singlet surface, this is called phosphorescence, right? I mean, I don't, from the top of my head, I'm not sure. But do the non-adiabatic terms also make this easier? Do you know this?
That is a very good question. I don't have an answer off the top of my head. But if phosphorescence is occurring, that sounds like there is radiation. So that may be done through a diabatic process. But I don't have the 100% answer for you.
Oh, okay. We can talk about this later, maybe. And now we have here also other professors. We have, as I can see, we have Professor, Marco Antônio Ridente. I would talk about you right now. Marco, por favor, pode fazer a sua pergunta.
Hi, Professor Lachlan. I really enjoyed your presentation. My question is not about the details of the technique, but I was a little bit curious about the laser, and I had some questions in mind. I think you mentioned, and I would like just to make some basic questions to understand better the system that you are modeling. So, if I understood correctly, this laser is produced by is excited by a diode photon that goes into a high pressure gas of a hair gas plus an alkali atom. Is that correct? And I was just curious to know if these molecules are just short-lived molecules that forms randomly and eventually interact with the photon. And is that correct also? That's another question.
Okay, very good question. So that is correct. We are diode pumping. So if we have our alkali atom, maybe it's rubidium. It has a ground state, and we've got the p manifold, and so we are pumping up to the excited state via a diode, right? So that is happening as radiative, right, or inverse radiative. It's absorbing a photon from the diode. And that's just the rubidium. That has nothing to do with the helium, although obviously the helium is in there. Why we need the helium then is so that we can then do the coupling, the non-radiative coupling. So now once we bring in the helium, right, as the helium comes in, now we don't just have this straight manifold, we then get the curves like this. And now as we get more coupling, and a coupling surface, might look like this to show the strength of the coupling, will get you to move non-radiatively from up here to down here. And then either the rubidium or the helium will take away that energy in motion. And right, calling this a molecule is a little bit generous, because even though we can see that there are valleys in the potential energy surfaces, the pressures and the temperatures that these are out there never going to stay in those valleys, right? So this is really, we call it a molecule, but this is really a scattering problem of a rubidium and a helium come in from infinity close to each other. We have a non-radiative transfer happen, and then the rubidium and the helium go back off to infinity. The helium is relatively unscathed, whereas the rubidium has now jumped or hopped from one energy surface to another energy surface. So yes, molecule is used very loosely here.
Okay, great. I think that was a very basic question, and you answered me very well. At least now I understood the problem. So it's actually a scattering problem. Okay, and you first pump the rubidium or the alkali atom, and then you study interaction between them. And just me to see if I really understood that. And after that interaction, the rubidium or the alkali atom, it will transit to another high state that can transit to the ground state and produce the laser beam.
Right. So yes, this is kind of, I guess this is kind of the picture of what's going on. Is the diode in number one, we have rubidium, and the diode is going to pump it up to that excited state. We then, in number two, that's when the helium comes in and we get the many-body interaction and we get the non-radiative transfer. And then step three, the rubidium is now down in this state. It moved from the top state to the bottom state, but still an excited state. And now
Okay.
we are going to stimulate the emission down to the ground state, and that's where we'll get our photon and lays.
Okay, perfect. Okay, so I think I got it.
So this is step 1, 2, and 3 is how the whole laser works. But really today I've just been talking about what's going on in step 2.
Yeah, I know that, but I would like to know more about the whole process, just to have the
Sure.
I know the big picture. And just as a matter of curiosity, what are the applications of these kinds of lasers?
Well, I think there are many applications of these lasers, just like you could think of applications for other kinds of lasers. I think an advantage of the diode-pumped alkali lasers are that they have the potential to be more compact than other, like a chemical oxygen iodine laser is huge, right? You can get a lot of power, but it's huge. But hopefully, again, we're still kind of in the early years for diode-pumped alkali lasers as far as being powerhouses. But there's a potential to get a more powerful laser in a more compact form. Having said that, I think anyone who has a favorite laser will say that about their laser, right? So small. If you wanted to use it as a communication device, right? If we communicating through lasers, doing quantum key encryption. If you wanted to use it as a weapon, right? Everybody talks about, hey, laser weapons, that's the future, and we've been talking about that for decades. But still, it certainly exists there, and as a Department of Defense entity, we're always going to talk about, can it be a weapon someday?
Okay, and just another very simple question: this helium rubidium system is in gaseous state? Is it a gas?
Yes.
Yes, and it must be a high pressure gas, isn't that true?
Yes. So I wonder. Yeah. So this is experimental data from the United States Air Force Academy, and you can see they were looking at 1,000, 2,000, 3,000 torr for the helium pressure.
Okay, so it's higher than atmospheric pressure.
Yes, I think so. I don't remember. I don't use torr a lot, so honestly, I forget the conversion to atmospheres.
Okay, I think it's 760. If I'm wrong, please correct me. But so it's a little bit higher. One at least 1,000, 2,000, 3,000 torr is higher.
Mm-hmm.
Okay. Thank you for your answers.
Well, thank you for your question. I appreciate that.
Ok, pessoal. Quem tem mais alguma pergunta, por favor, fiquem à vontade aí. Bom, pessoal, então, espero que todos tenham gostado assim como eu. E eu vou dar um encerramento aqui. Lachlan, muito obrigado pela sua apresentação, muito legal. Bem-vindo aí à divisão de Ciências Fundamentais. Espero que os próximos 3 anos sejam frutíferos aí para você. Eu queria agradecer mais uma vez, queria que todos abrissem o microfone para agradecer mais uma vez o Major Lachlan pela apresentação aí. Muito obrigado.
Obrigado. Um prazer foi meu.
Bom, pessoal, muito obrigado. Então, até a próxima.
Até mais.
Obrigado, boa tarde.